Bismillahirrahmanirrahim. Hello students, welcome to the electrical engineering channel. In this lecture, I am going to discuss non-linear regression models to fit non-linear experimental data. So in the previous lecture, I discussed the linear regression model because the experimental data set which was available to us had the shape of a linear variation. So the dependent variable was varying linearly with respect to the independent variable. But if our experimental data has non-linear variation, for example, an exponential variation, then we have to use the exponential regression model. So exponential regression model has this type of general representation: y is equal to a e raised to power bx, and here again we have two unknown coefficients a and b. So here we will again first find the residue, which is ei equal to yi minus a e to power bxi, and the least square error method will be applied over here. So these residues will be squared and added for all the dead points. So SR equal to summation I is equal to 1 to n ei square, and it is equal to summation I equal to 1 to n square of this expression. And we have to first take the derivative of this expression with respect to a, and we have to take the derivative of this sum of the errors with respect to b and equate them to 0 to calculate the minima of this summation. So this is the first term, this is the second term, and after simplification and readjustments, we get this expression, right? So this 2 actually has been taken to the right hand side and equated to 0, and this will become minus yi e to power bxi plus a summation e to power 2bxi, right? So this exponential term will be multiplied with these two, both the terms, and this 2 will be taken to the right hand side. So this second equation will become uh, uh, yi into xi e to power bxi minus minus plus and a summation e to power 2 bxi. So these two exponential terms will be multiplied together, and in this case this 2 and this a will be taken to the right hand side to equate them to 0. So these are the two terms, and from these two equations we can find out the equation for a, and this equation of for a is actually evaluated from the second equation, and from this first equation actually. So this a is equal to this summation divided by this summation. Now we can substitute this value of a into the second equation, and this second equation will become this summation minus this expression for a multiplied by this summation. So this is our final equation, and we can see that this is a nonlinear function, and in this nonlinear function we actually have only one unknown variable, which is b. So first we will calculate this value of b by using nonlinear models. For example, Newton-Raphson algorithm or bisection algorithm. By using these algorithms, we can calculate the value of b because this is a nonlinear function. So after calculating this value of b, we can calculate the value of a by putting the value of b in this equation. So these values of a and b have to be calculated by using nonlinear algorithms, and those nonlinear algorithms we already have discussed previously, and now I will show you how to apply those nonlinear algorithms to calculate these coefficients. So this is what I have discussed so far, and you can also see the same set of expressions in this manual. These are all the equations, and this is the first coefficient a, and this is the final nonlinear equation, and this equation will be used to calculate the value of b. And we are given this exercise in which the values of t and gamma are given to us. So this t is given in hours. This gamma is actually the relative intensity of the radiation. So this gamma is actually the relative intensity of radiation, and we have to evaluate this nonlinear regression model. So gamma is equal to a e raised to power lambda t. Values of t and gamma are given, and the values of a and lambda are actually unknown. So lambda is actually the decay rate, A is actually the coefficient, and we have to find out the value of the regression constants A and lambda. So let's start discussing the MATLAB algorithm, and we have to first build up this function, which is actually our final nonlinear equation or nonlinear function. So we have to first build up this equation in a separate MATLAB function, right? So here you can see that these are actually our four summations: f1, f2, f3, and f4. So this is f1, this summation is f2, this is f3, and this is f4. And we have to initialize these four functions of the summations from 0. And this is our t, this is our gamma, and x is our unknown variable, which is actually b in this case. So here b is actually x, and we have to use a for loop, and this for loop will be repeated over the total number of entries or total number of data sets. So our data actually contains actually 6 points. So this for loop will run 6 times, and this is our first summation: f1 equal to f1 plus gamma is actually our yi, and ti is actually our xi, and this x is actually our b, right? And xi is actually our ti. So this is our first summation. This second function is actually this summation. Yi means gamma I into exponent bxi or xti. This is our third summation, exponent 2 into x into ti, and this is our fourth summation. F4 is equal to f4 plus ti, which is actually our xi, and exponent 2x into bxi. So this summation is actually evaluated in this for loop. So when I use f equal to f1 plus this expression, it will, in the first iteration, it will add 0 to this expression, and it will evaluate some value of f1. In the second iteration, this f1 will be added to the next calculated value, and those two calculated values will be added again in the third calculated value, and in this way we can evaluate these summations in MATLAB code. So after that, this is our final function, and it is equal to f1 minus f2 divided by f3 multiplied by f4. So this is how we can build up the nonlinear function in a MATLAB function m file. Now I will use this function m file in the separate main file, and this actually main file will use either the Newton-Raphson method or the bisection method to calculate the values of this b and a after some iterations. So this is our MATLAB script, and this is the first function m file that I have already discussed. And in the first case, I will use Newton-Raphson method to solve this nonlinear equation. So this is our symbolic math toolbox, and x is our unknown here, and these are our time values, these are our gamma values, this is our function, which is actually built up using this separate exponential m file, and I have to use these values, and I have to pass these parameters from this exponential m file, and this is the derivative of my function, which will be used in Newton-Raphson iterations. This is my initial guess, and here all the steps are the same which we discussed previously in solving nonlinear problems using Newton-Raphson method. So this is my error. So I have specified the tolerance of 10 raised to power minus 6, and this is Newton-Raphson algorithm, and I have used two errors, and I will use the maximum value of these two errors, and this is actually my next iteration condition, and this is our count is actually used to calculate the number of iterations in which the solver has converged. Now after solving this nonlinear algorithm, I will display the calculated value of lambda. So the calculated value of lambda is actually the same as the value of b, right? So this is my nonlinear regression model, and here the value of b is actually the same as the value of lambda. So then I will display the total number of iterations. Now I have to calculate the value of A. So here again I have to use two summations for calculating the value of A, because when I have the value of B, I can calculate the value of A. So by using this value of B, I will again evaluate these two summations, F2 and F3, and A is equal to F2 divided by F3. So you can see that this is F2 and this is F3, right? So this will give me the value of A, and then I will display the value of A. Then I will plot my experimental data on top of the regression model, and I will make the comparison. So let's run this algorithm, and after running this algorithm, you can see that this is my experimental data, which is shown by blue sterics, and this straight line is actually the regression model, and you can see that all the experimental data points are satisfied by the regression model, and the calculated values of lambda a and number of iterations are also displayed over here. So the same can be done by using bisection nonlinear algorithm. So in bisection nonlinear algorithm, this is my algorithm. Again, these are the same data sets. This is my function, and in bisection method I have to specify the two boundary points, and we have to be sure that our solution exists between these two boundary points, and this is my specified tolerance, and this is bisection algorithm. After implementing this algorithm, I will display the values of lambda and total number of iterations, and then I will you calculate these two sums f2 and f3 to calculate the value of a, and then I will display the value of a, and then I will print, or I will plot my regression model on top of the experimental data. So let's run this algorithm, and here again you can see that these are my calculated values of lambda and a. Here I have, it has taken 7 number of iterations, but the final plot is exactly the same as we obtained for the Newton-Raphson method, and it is in absolute agreement with the experimental data. So in the second part of this activity, we have to calculate the half-life of the technetium-99m and radiation intensity after 24 hours. So these are all very simple. These are our calculated values of the coefficients, and by calculate to calculate the half-life of this material, we have to use this expression, and gamma is should be actually equal to 1 by 2 of gamma at 0. So by using this as a condition, we can calculate the value of t. So t will be the half-life if we use this condition. So this will be equal to this, and after solving this equation, t is equal to 6 hours. And in the final part, the radiation intensity after 24 hours have to be calculated. And this is our final expression for gamma after calculating the values of a and lambda. And by putting t equal to 24, the value of gamma is equal to this, and in percentage it is actually equal to 6.3171%. So t is already actually given in hours, so we don't need to convert this 24 into seconds, because we are already given time in hours, and these are our plots of the regression model by using Newton-Raphson and bisection methods. So that is all about our today's discussion on nonlinear regression. I hope you have enjoyed and understood the contents of this lecture. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.